All right. Good afternoon, everybody. My name is Rayan Chikhi. I'm doing my second CGSI presentation. I did a presentation last week for those who were not here on KMR data structures. I should speak closer to the mic or just more loud? Okay, good to know. So today we'll talk about metagenome assembly methods. And small disclaimer, I'm a CGSI for my first year only, so this is not an example of what a tutorial should be, maybe. So I was admirative this morning that Ben was actually running code and nothing crashed, right? It all worked. He was even downloading from the internet and a large file apparently, so it's impressive that he was able to do all of that. I will do nothing of that myself. This is going to be a static presentation for 30 minutes. You can just hear it. And then during the last 15 minutes, we'll do a small exercise with a pen and paper. So if you don't have paper, try to find one from your neighbor, or maybe some people have stacks of paper to share. Right, so let's get to it. So the problem of metagenome assembly, probably most of you are either working on it or know about it. Who's not too familiar with metagenome assembly? 2, 3 people. Okay. So for the 2 lucky of you, I'm going to recall what the problem is. So it's a problem of reconstructing a set of genomes from species. And so usually it was the genomes that was reconstructed, but you can also go as far as reconstruct the strains, so small variants between the genomes. And typically the type of data used is short-read sequencing from an environment, so soil, human gut, human skin, and so on. So the process is you sequence some data using short-read sequencing, you obtain some reads, and then one typical step is to either align the reads or produce an assembly of those reads. And typically the situation that we are concerned with is when your alignment of either the reads of your assembly doesn't match the reference. So in some cases, when you're lucky, most of your sample can be mapped correctly, like 90% or more of your reads. But in metagenome setting, it can happen that you have less than 50% or even less reads or contigs that match. So if few reads match, there's a higher chances that contigs might match to the database, but it is not even certain. So the process of assembly is trying to actually get some genes, so get an approximation of the genomes in your sample, which is hopefully going to give you to a better idea of what is inside your sample. Can you still hear me this way, or should I speak louder? Very hard? Okay. Oh, actually, it's directional, so maybe like this?
There are also plenty of seats down front where it's much easier to hear. Yeah, no, you guys come down.
All right, I'll do my best to try to shout, but I'm afraid I might make the people in front of the rows deaf, so. You guys figure this yourself. I'm gonna have to do a talk here. So, okay, challenges. So there are a few challenges for doing metagenome assembly, which are specific to metagenomics on top of the usual genome assembly problems. And those are closely related strains, so genomes which look like each other, uneven depth of sequencing, low depth of sequencing. There's also repeats, which are not just inside a genome, but also between genomes and between strains. The size of the data set is typically much larger than genome data sets, and also the lack of long reads. So typically it should be possible to sequence using long reads or long range information, but the data is not very standard yet, so there's mostly Illumina sequencing for metagenomes. So all of these have been adapted from a talk from Anton Korbenikov, and oops, it's going to come back in a second, hopefully. I guess the system just shut down on me. Your laptop is still on, and it's back. Thanks. Okay, I'm not touching my laptop anymore. So this is a sketch of the type of repeats that you can see in metagenome. So repeats which are within genomes, so circles are genomes, and repeats which are in between genomes with synteny blocks or just gene transfers. So it's a mess to assemble, and as you can imagine, the assembly quality of metagenomes is less than genomes. All right, what comes after assembly? So this is not exactly my expertise, but I wanted to touch upon the later steps. So after you have an assembly, what's typically done is called binning, which consists of taking contigs and trying to get bins of contigs which putatively correspond to the same species or the same strains. And there's a number of software for doing this, Concoct, Metabat, and so on. And another step then, after you have done binning, is to do taxonomic identification. So try to find which species your group of contigs belong to, or even some strains. Again, there are some software that do this. A nice review, which I will talk about later, which evaluates assembly, binning, and taxonomic identification is CAMI. I'll talk about this more later, but also another pointer. I don't see easily my slide here, so I have to go back and forth, maybe. If I do that, I'm too far away from the microphone, right? Yeah, so, right. So another pointer is the NVO pipeline, which is actually a wrapper around assembly, binning, and taxonomic identification, and I think you will have a talk about this in a few days. So I'll focus on metagenome assembly software. And the landscape is, as you expect, there's a number of methods. I've put in bold the top 3 methods in my opinion, and 2 references corresponding to the papers. My own method is called Minia Pipeline. It's not published, but I'll talk a little bit about this. And actually, to be honest, my opinion is to get a good overview of the state of metagenome assembly nowadays. It's sufficient to read those 2 papers here, so Nork et al. And Lee et al. from 2 years ago. And so if you have read them, then good for you. If you have not, then I will give you a summary, a little bit of the important ingredients, in my opinion, from these papers in this presentation. So this slide is a high-level overview of how a genome and metagenome assembler works. It starts in a simple step, which is to construct a graph. And typically in a metagenome assembly, it's the Bruijn graph. And then there are a number of operations being done on this graph. First is that the likely sequencing errors are removed from the graph. And also then variants, typically SNPs, small indels, are identified and removed from the assembly. So this has an important effect, which is to collapse strains. Okay, I'll have to touch my laptop just to see if the pointer works. Yes, it works. Okay, it's risky. And finally, after these simplification steps, contigs are returned as simple paths, so paths without branching, from the simplified graph. So there's a usual, not a usual, but sometimes a misconception in assembly software, where in some papers they say that they find some paths in a graph, some Eulerian path, or actually some traversals. In practice, this is not exactly done this way. In theory, this is in fact an actual valid model, but in practice, what is returned is not a path in a graph, but a set of paths corresponding to contigs, which do not cover the whole graph and provide an approximation of the metagenomes. And finally, after all these steps, contigs can be further improved by doing repeat resolution using pen and reads, or using long reads. So there are some repeat resolution and scaffolding steps that come after. During this talk, I'll mostly focus on the first 4 steps, because actually that's where many of the heuristics and many of the critical choices are being made for quality of assemblies, in my opinion. To illustrate, I'm showing you a pipeline of an actual assembler called MegaHit. And from this pipeline, there's a lot of stuff, but on the right, I'm showing you the correspondence to the previous slide. So these 2 steps correspond to graph construction. So we also build the Bruijn graph. The step here corresponds to simplifications, removal of erroneous k-mers and also variants. And finally, the last step is output contigs. There's a bootstrap step here, which we'll discuss later. I definitely should not touch this computer. So basically, in this slide, we are looking at an actual assembly pipeline. Oh, what? All right, okay. I'm not touching this anymore. So just to show you that it's actually a common framework, this is another assembler, Metaspades, which also follows the same paradigm. So it starts from the reads, constructs an assembly graph, and then there is much attention which is dedicated to actually doing repeat resolution using one algorithm called expander, and also recovering the strains, and a special treatment for the strains in the right side of the slide. And so everything I'm going to talk about is kind of masked in the first step of this assembler, but it follows the same structure essentially as what we've seen before. And in the end, contigs are returned. And finally, a third pipeline is my software, so Minia. It also works in a similar way. So it starts by taking the reads, correcting them. And then we have a set of tools which have a lower grain than perhaps other assemblers. And the purpose here is to make the steps a little bit modular, so being able to run independently with different parameters, some of the steps, like k-mer counting, graph construction, and being able to inspect the intermediate results, and maybe switch modules with some other modules with different parameters to have a higher control on the assembly that you obtain in the end. So being able to tune whether you want to collapse all the strains or preserve most of the strain information. In many assemblers, it's not very straightforward to do this. And when we designed this one, there was a focus on being able to do that. So I'll come back to this aspect. This slide, you probably have, many of you have already seen this one. So that's a definition of the Bruijn graph, which is common to all the assemblers we've seen so far. So it's a graph which was introduced by a mathematician a long time ago, and was used a less long time ago by informaticians, Pavel, which is here, and others as well. And there's multiple definitions in the literature. The one I use here is, in my opinion, the most simple one. It's where the nodes are k-mers present in the reads, and the edges corresponds to exact k-1 overlaps between the nodes, between the sequences of the nodes. So there's a simple example in this slide where you see a bunch of reads, so 2 reads here, which contain a small variant. In between them, it corresponds to a nice, what we call bubble motif in the graph, which are 2 paths starting and ending at the same node. An interesting aspect of the Bruijn graphs is that they preserve some repetition. They show some repetition structure whenever a repetition is exact and longer than k. So in this set of reads, there is a k-mer CTG, which is, as you can see, is repeated within the genome. What happens in the graph is that you have a cycle containing the k-mer CTG. And because of these repetitions, which are very common in the Bruijn graph from genomes and metagenomes, the graph is difficult to traverse. And that's one of the main reasons why assemblers cannot just output a single path in a graph, but have to decompose the graph into subpaths. So I've shown you the Bruijn graph, but actually an object that many assemblers work with are compacted graphs, where they take the Bruijn graph and take the paths which are unambiguous in the graph, and then compact them into single nodes, and you obtain this representation. So it's mathematically equivalent to the Bruijn graph, but it's just simpler to work with. So we call these nodes unitics, and there's a few things which happen. So there is no loss of information between the Bruijn graph and compacted graphs. Compacted graphs takes less space, but the downside is that they are slightly less easy to update. If you want to insert a k-mer, you might break a node into multiple nodes, and so on. So it's not clear exactly which of the two representations is better to work with, but the consensus so far was that compacted Bruijn graphs were interesting in cases where there was no need to update the graph. So typically metagenome assembly. So this is what the graph from metagenome looks like, visualized using the very nice Bandage software. This one is a small metagenome, so it has in total, I say total length at 18 megabases. It has 50,000 nodes. You can see that each component, it's tempting to say that each component is a genome. It might be true for the first 2, and maybe some in the middle as well, but the small components are definitely parts of genomes which have been split into multiple components due to lack of coverage. There's a lot of what seems to be noise at the bottom of this figure. Some of it is noise, but some of it is also small parts of genomes corresponding to low abundant strains or species. All right, sorry, I didn't define it. So each line that you see here corresponds to a node in the compacted Bruijn graph. Longer the line, the longer the sequence of the node. So what you would like in the perfect sense is to have as many lines as genomes that is present in your data set. Unfortunately, first of all, these are not lines, these are actually graphs. That's because there's some repetitions in the genome, so as soon as there is a sequence which is exactly repeated in one of the genomes, then it creates a branch in the graph, so that's why you see those branches. And second of all, there's many components because of lack of coverage. As soon as one chimer is missing from the reads from one of the genomes, then it breaks down into as many components as missing chimers, essentially. Oh, the rows, sorry. The rows are actually artifacts of drawing the graphs. Software wants to display this graph on a screen, and in fact, it has no way to determine whether one component corresponds to a genome or not. So it just tries to place them in a nice way. So the bigger components are on top, and then the smaller ones are at the bottom. This has no biological significance whatsoever, except that we can link, in some ways, the bottom ones to low coverage and the top one to likely high coverage, high enough coverage for assembly. Oh, on the right part, I'm guessing this is also a layout effect. So just to maximize the amount of information shown on the screen. So it's really tempting to draw some conclusions from how the graph was drawn. I would really avoid doing so and actually just take it as a visualization. There's many ways to draw a graph. This one is one of the possible ways. So it's software dependent. So here's a little zoom so you can see for the smallest components, they are typically just one node. And the way they are drawn also sometimes is just squiggly lines. The angle of the line doesn't mean anything. It's also just an artifact of drawing software. I find it interesting to actually understand what is in your data set in a visual way, to visualize the assembly graph, and I think it's not enough done in data analysis. So typically you compute statistics on the context. It's also nice to visualize context sometimes. So yeah. In that specific assembly, see last graph. So yeah, this is a velvet assembly. Yes, each thread is a config. So the longer the thread, the longer the config. All right, so this talk is actually under the hood of Metagenome assemblers. So we'll talk about 3 different aspects. One is a MultiK. Other one is low abundance recovery, rescue. And the last one is how we actually remove sequencing errors and strain variants from the graph in order to obtain an assembly. And I believe these components are critical if you develop metagenome assembly software, but I believe they are also very interesting if you run an assembly software to understand what it is doing behind the scenes and why you are not recovering the genomes you want or the strains that you are interested in, and what were the choices made by the software. The first interesting point is to observe the effect of chimer size. So if you run a single genome, so this is an isolate Salmonella, using an assembler, Velvet, from Illumina reads, the assembler asks you for a chimer size, and it's not always easy to predict which best chimer size to use. And it's nice to observe what is the effect of changing this chimer size. So with k equals 51, you see a big mess, but it's still a single component. The effect here is that many repetitions are happening in the graph. And because of that, then it's hard to create long contigs, and there's many branching. And the layout algorithm is a little bit lost, so it does a big hairball.
Right. But
yeah.
The K is unrelated to the Illumina. The K is for the assembler.
Yes.
Okay. And still with K51, you get.
Yeah, surprising, huh? It just happens that in genomes you get, there's not so many repetitions, but they are enough to make the graph look like this.
These are not statistical repetitions. They are genomic.
Yeah. Well, there are some statistical, but I don't know what is the, I mean, there are just many repetitions in genomes in general. And for 51, this is what happened. Well, let's observe what happens when we change to k equal to 61. That's a very small change in terms of values, but you see that the graph becomes significantly more manageable to observe and possibly resolve. Let's continue and then go to 71. And I think this is going to be more or less the optimal one, because we see still a single component and much less branching than before. And finally, if you're tempted to increase k again to, let's say, 81, then the graph gets disconnected into multiple components, indicating that the sequencing coverage was too low to see all the 81-mers in the reads, all the genomic 81-mers. So if you, yes? I'll talk about this right after, but this is just what happens if you naively construct. I mean, naively, I say naively, but in fact, assemblers have been doing that for a long time. Construct from a single k value. I mean, if you observe this, it's natural to ask the question, can we do better? Okay, and finally, this is k equal to 91, clearly not a good assembly. All right, so the remedy that has been found 8 years ago, introduced by Peng et al. In 2010, is to do MultiK. So the idea is that you will reap the benefits of multiple k values. And the principle can be summarized in this figure. The first step is to run the assembler with a small k value. I think here is 21. And then take the results of the assembly context and feed these results as well as the reads again to your assembler with a larger k value. That way you preserve connectivity information from the small k-mers into a larger k-mer size graph. And finally, you do this for many k-mer sizes. Here I'm just showing 3, but some assemblers do it with more. And if you want to have the most contiguous assembly possible, it would be nice to do it from 21, 22, 23, and so on. But due to running time constraints, you cannot do that. So that's why assemblers typically select a handful of k values. So let's have a look at what is the effect now. So I've run an assembly of the same genome as before using a different assembler, Spades. But as you can see, the graph looks a little bit the same with k equal to 21, many repetitions, many branchings. And Spades actually is a multi-k assembler. So it can do what I showed in the previous slide. So if I run it with k equal 21 and then feed the results to k equal 51, 55 here, then we obtain a graph which is visually better, less branching, still one component. And then we can go further and try, let's say, k equal 99 by feeding the results of the k equal 55 assembly. And as you can see here, the graph remains a single component, slightly less branching as before, but we don't observe the disconnection effect that we see if we run the assembly with just a single k. So a single component is actually what you want to aim for if you want to assemble an isolated genome. Of course, if it's a metagenome, it will never be a single component except in cases where the genes are shared between your species. So okay, I just wanted to show you some nice MultiK graphs. And now I will switch gear a little bit and talk about data structures for one slide, because I love data structures, so I can't avoid talking about this. One question which you might or might not be asking if you know metagenome assembly, there's an assembler called MegaHit, and it's very fast. You can assemble metagenomes in a matter of days for the largest ones, let's say soil metagenomes. And why is it fast? It's because of some very nice computer science behind it. And here I'm highlighting just 2 effects. One is that it has designed a data structure which indexes the reads in memory and does k-mer counting implicitly. So it can count k-mers from reads with multiple k value by not having to read all the reads again from disk many times, but instead querying a data structure. And this structure is called succinct Bruijn graph. And it has also a carefully engineered construction here. So here on the left, you have the Bruijn graph using their own definitions. So k-mers and edges are k plus 1 mers. And what the structure does is that it inserts the k plus 1 mers in a sort of a Burrows-Wheeler transform / FM index data structure. It's not exactly a Burrows-Wheeler transform because here the k-mers are actually sorted in a reverse lexicographic way. So you don't see the LF property for those of you which are familiar with it. But there is some sort of a LF property. I'm tempted to use the pointer, but let's see. There's some sort of a LF property with respect to the last column, W, and the second to last column. So here, if you see T corresponding to the k-mer ACT, is actually the T here corresponding to the prefix ACT. And the first C corresponds to CAC, which is also the first C in the last, second to last column. So it's not a first last, but the last second to last property. So it's actually a Burrows-Wheeler over K-mers with some tricks. And what is stored is W, the last column, the tip column, and F, which is a summary of the alphabet. So essentially, with just, if you count the number of bits necessary, it's just 6 bits per K-mers, plus K plus 1 mers. So it's very memory efficient, and it allows to do some nice operations. So maybe I'm going into way too many details for this tutorial, but it's to give you a feel of the type of computer science that goes behind metagenome assemblers for the sake of being efficient. So some really nice CS over here. Yeah.
I don't see the former CTAC.
CTAC. Oh, you're right. There is no CTAC in this structure. Oh yeah. Oh, wait, there is here. But one here. CTAT is not in the data set. So you got CTA node here, and it goes to TSE. No, actually, if you have two nodes, CTA and an edge to another node, TAC, then the shared prefix is TA. Yeah. No problem. Any other question? It's directional, yes. The graph is directed, and it's always the case in genome graphs. Yeah. Yeah, I'm quoting the paper, and the 6 bits are coming from. So you need 1 bit per K-mer for tip, 1 for last. For W, you need 4 bits because you need to store the alphabet plus the dollar symbol plus the minus sign. So that's 2 for the nucleotides, 1 more because you're rounding with a dollar sign, and 1 more for the minus. Maybe you can be more clever and do 5, but that's how they say. So, and F is negligible. It's just side of the alphabet. So they do some nice handling of, I think the critical aspect here is the dummy nodes, like the dollar signs, which have been inserted because you need to track in the graph whether a node has a neighbor or no neighbor. And okay, I will not go into this consideration. It's way too technical for the rest. But okay, I'll stop here for mega hit. So graph simplifications. You don't need to check out the gray stuff yet. I just want to highlight here. I'm actually showing what Spades is doing. The typical things which are done in assembly graph simplification. So tip removal consists in finding nodes which have no connection on one end and connected to the rest of the graph on the other end. And there are some criteria on their length and their coverage. And those correspond typically to sequencing errors. The rest is bulge removal when you find also nodes which are in this type of shape corresponding typically to SNPs. There's also bubble removal, which I will not talk about. It corresponds to this type of events where you have no branching in both paths. And finally, there's one more I will not talk too much about. The reason why I'm showing this slide, which is a little bit technical, is to show that actually there are not so many advanced statistics in this graph simplification procedure. It's all decision based on inequalities. And maybe there could be some room for improvements here because it could be possible to maybe model the sequencing process and inform the assembler a little bit more. But so far, no one has done that. The reason I suspect is also because those simplifications are deeply buried inside the assembler, and it's hard to take them apart and try to play with them. So you kind of have to take the whole code of a big software just to isolate this section. And actually, what we did was take these components and provide them as an independent module that acts on assembly graphs. So we think it's possible to maybe play with these parameters in an easier way that way. Okay, 30 minutes, I should go a little bit faster. One more interesting thing is how to deal with a flood of erroneous K-mers. So in your sequencing data, Many k-mers correspond to genomes, but many k-mers have error in it. And in the Bruijn graph framework, k-mers which have errors, you don't want to deal with them. They typically are thrown away in the graph simplification procedure. So when you do that, assemblers typically try to correct the reads, but once they are corrected, there are still some erroneous k-mers remaining. And so what you want to do in order to be conservative but also keep many k-mers is do one of the two alternatives. So megahit, what it does is keep k-mers which have been seen at least twice, and tries to recover some of the k-mers seen only once using mercy k-mers, which I will talk later. And the Spades assembler has a drastically different approach when it keeps everything after error correction, and then try to simplify a little bit the graph before it is constructed to avoid using too much memory. So this is mainly for performance, but it's, I think, a critical aspect for dealing with complex metagenomes, because you have a trade-off between being able to process all of your data using your server and also make some heuristics in order to not lose too much of your assembly. So also I'll talk about some alternatives. So we provide a standalone software for doing simplification on the graph before it is constructed. No, after it is constructed, so that's deep clipping. A standalone mercy k-mer module. And also last year I tried to do pre-simplifications on a graph when it was partitioned by minimizers, but I will just mention that it's not a very effective method. All right, mercy k-mers. So that's a technique that is used by the megahit assembler, and I think it's quite elegant, so I'll talk about it here. So when you construct a graph, the Bruijn graph, so for instance this one, the original one, it may happen that some nodes are disconnected because the k-mers have been eliminated due to their low abundance. What the mercy k-mer approach is when you have some reads which has two solid k-mers and some non-solid. When I say solid, non-solid, it means passes the abundance threshold or doesn't pass it. So k-mer is not seen enough in a data set. When some of the k-mers are not seen enough, but some reads can still rescue them, then the mercy k-mer does what you expect. So it inserts those k-mers back to the graph in order to reconstruct connections between two components. So that way it's possible to assemble very low abundance genomes because some parts are supported by solid k-mers. So that's a neat trick. Yeah. That's a great question. So they were filtered initially at the beginning because the assembler cannot afford to keep all the k-mers, even those seen only once in the graph. If it did that, it would consume way too much resources. Yes. So we introduced this trick to be able to at least recover some of the critical k-mers. Okay, I'll mention scaffolding. So this is going to be a quick slide because, first of all, I'm not an expert in this one, and also there are not so many metagenome scaffolding software. I haven't written about them, but Bambus is one. There may be others, I don't know. It's the same as genome scaffolding. So when you try to order and orient contigs in order to recover a longer genome structure, except that here in metagenomes, it's possibly to place contigs in multiple scaffolds, not just one scaffold. So in my opinion, there are no good and efficient standalone metagenome scaffolders, but assemblers find another way. And in Metaspace, for instance, they use a model called repeat resolution, which does some sort of scaffolding in a different way. And megahit use a local assembly module, which also does use paired information, but not exactly for scaffolding. So I was interested in actually understanding the inner components of assemblers, of metagenome assemblers. So what I did was dissect the megahit software by just trying to isolate component by component what it was doing and the effect on assembly quality. So taking one data set from the CAMI benchmark, which is a metagenome assembly benchmark, I run megahit with just a single k value, so without multiple k, without mercy k-mers and using only single land reads. So it gave me this assembly size, which is 300, little short of 300 megabases, and a low N50. But when you switch to a multiple K strategy, you see that assembly size increases and N50 also, which is unsurprising, but it's good to see the magnitude of the effect. Oh yeah, I didn't define N50. So that's a classic genome assembly metric which evaluates the size of your contigs. So higher than N50, the longer your contigs are in general. So it's related to a weighted average of the contig size. So you want to maximize N50, and ideally N50 should be the genome size, but in practice it's never the case because contigs are always shorter. So here N50 is very small, but that's kind of typical of what you get with the genome assemblies. So then you can see that if you keep using more modules, such as mercy k-mers and paired information, then assembly size increases and N50 increases as well. But what I want to highlight here is that even a simple assembly with just multiple K already does not so bad at recovering most of the metagenome with a reasonable contiguity. But of course, the later modules are still improving. I skip this one, it's about graph formats. I skip this one as well about handling reverse complements, you can just read it. I'll just mention evaluation of assembly quality, still under the metaphor of under the hood assemblers. To evaluate assembly quality, there's the usual genome assembly metrics, which I will not have time to define in too many details, but there's N50 and G50 total size of the assembly. You can map the reads back to the assembly to see a percentage of them which map correctly, predict the genes, and also try to match contigs to the known reference in databases. There are some metagenome-specific assembly methods, which I list here. MetaQuest is one. CheckM, which recovers some marker genes from your assembly and try to improve it by by using the fact that marker genes may belong to the same species or the same group of species. And finally, Valet is another evaluation tool which try to determine concordance of paired end reads in bins of your assembly. So all of this is to evaluate how good the assembly is without any reference. So of course, if you had a perfect reference, it would be trivial, but that's not the use case of genome assembly. I'll mention one benchmark, which is very recent from last year. A community of people have created artificial synthetic metagenomes and asked the community of genome assemblers to assemble them. So six assemblers were evaluated on 3 artificial communities. And in the paper, they actually reported results on the largest one. So this is a dense slide, but it shows essentially how good assemblers can perform on a high complexity metagenome dataset. And what I like about it is that they stratified the results in 3 categories. So all genomes, genomes which have high similarity between them, and genomes which have low nucleotide identity, so low similarity between them. The intuition here is that genomes with high similarity, so B, correspond to strains of the same species, and they are harder to assemble because typically assemblers remove variation. And as you can see, actually, the fraction of those genomes in B category is much lower to the A and C categories. So some assemblers, namely Meraga, which is a variant of Megahit, Megahit and Minia, perform well on genomes which are not too similar between them. But for the other methods, it's clear that it's a little bit harder to reconstruct those genomes. But here it's just genome fraction that was evaluated, not the contiguity. I just mentioned that Minia was designed to be efficient, so it's faster than Megahit. So it's less memory than Megahit, but fast, but same speed. Metaspades was run, but consumed too much resources, according to the organizers on this large dataset. At the time, I think now maybe it could possibly be able to run it because they improved quite significantly the performance of this assembler. And the conclusion of this benchmark was that reconstructing strains was very challenging. So that's possibly the next frontier in terms of metagenome assembly development. Metaspades is attempting it, but in the general problem seems to be very hard. Yes? Yeah. in fact, in the raw graph, you can see the strains, but it's the same as phasing, essentially. So you have some, you know the differences, but it's hard to know a connection between two differences which are far away in the genome, because there is no read that spans them in the general case. So essentially, what assemblers do is, in a naive way, they remove all the differences and keep only one consensus. Metaspace, what it tries to do is try to recover some of the linking information between strains observed in the graph. But the general problem is hard because it's hard to phase variance across many strains. By phasing, I mean linking one variant to a strain and keeping this information consistent across the whole graph traversal. I realize it's a very blurry explanation. Maybe I'll do a better job offline. Okay, how much time do I have left? A couple of minutes? Not so much minutes. Okay. I'll skip that one, and for a few minutes, before I do my conclusion, I would like to propose to you to do a small exercise in the spirit of this tutorial. Here are 8 chemers, and I've hidden 2 strains in this data set. I would like to propose to you to try to assemble them and find the DNA sequence of the 2 strains. So for this, you clearly need a pen and a piece of paper. I think it's hard to do it by just eyeballing it, but you can try.
Yeah.
So I started the timer before I started speaking. It says 41 minutes, so that's why I was confused.
Yeah, no, I think we're right on time.
Okay. They really wanted to do this, at least for the sake of them trying to. Yeah. No, you can. You feel free to give one on the spot if you have one, but. So the first one who finishes can just shout the sequence, and we'll see if it's correct. Yes?
2 sequences.
Yeah, 2 sequences. I don't think so. Two strains, so you should expect similar sequences with small variation. But it's not easy. If it was easy, then I need to peek on my laptop. But you won't be able to see. Did you say TAGT, CAT? You're correct for one of the 2, yes. What is the other one? No. Well, TTG is technically a 3rd strain, but it's too small to be just. It's just 1 chemer, so it's not much. TTG is a trap. You're supposed to discard it. You can see that this chemer is connected to nothing, in fact. There's no connection to TT or to TG, so. I'll maybe move along so we can keep being on time, right? So I think you were already close enough with this attempt. Anyone has a proposal for the other one? If not, I propose to you this graph, which is the Bruijn graph for this set of chemers. So what you see here is actually it has 2 start points. So one is TAG, and the end point will be CAT. And then there is one clear path, so from TAG to CAT, which spells the sequence that you just gave me. So it's TAG, TCAT. And then what's happening here is that there's another path that goes here, but there's a gap. I purposely removed one of the k-mers from the data set, which is GAC, which if there was GAC present, then you would have been able to reconstruct this path, which corresponds to the strain TAG-ACAT. And that's a very common situation in metagenome assembly. And how do you deal with missing k-mers? You see that visually you could infer that one k-mer is missing, but when the graph is too complex, then typically assemblers don't do that. They never infer missing data. And TTG was just separated from everything else, so it was a different component. All right, so I'll wrap up here. So by the way, the slides will be available on my Twitter account in a few minutes. What I wanted to convey was that metagenome assembly is a difficult problem, and also evaluating genome assembly is difficult, multiple metrics. The problem is difficult due to presence of strains and low abundant species, mostly. And it's possible to have a trade-off between contiguity, genome fraction in these assemblies, but it's hard to be able to have a high contiguity and also keep a lot of the genomes in the data set. That's one of the parts I actually skipped, but it's a side effect. So I note limited availability of long reads so far. I'm guessing there are some data sets, but not as much as short reads. Some pointers on some references and some acknowledgements. And I just mentioned that if you're interested in doing a postdoc in France, just talk to me. All right, thank you very much, and have a good CJSI.
So in a sense, there are some metrics that are specific to metagenome. Do they have a notion of how far the data is, or are they also so you just send those to Rayan, because the other countries there's a sort of
Right, so I'll go back to the slide that is this one. So if you put together two stretches of sequences which should not be together, then Valet aims to detect this. And if it happens by chance that what you are doing is in a reference data set, so it was part of a genome which was previously sequenced, then MetaQuast should be able to report it. But this is in a controlled fashion. You might be able to detect it by looking at the percentage of looking at the reads mapping back to your assembly and noticing that some of the paired end reads will not support this contig in its entirety. But overall, my opinion is that methods don't do a good job in a general setting, so without a reference database. It's very hard to evaluate this type of event. Yeah, this is a good remark, and I think it also ties into the simpler problem of assembly where you believe that you have assembled a genome. In fact, many of the repetitions were collapsed and so on. So the problem is more dramatic in metagenome assembly, yes. All right, thanks.